Welcome to this webinar of our latest series. And first of all, I would like to introduce you our speaker for today, Professor Ivan Minev. So, hi, Ivan. Thank you for being here. Just a few words on our speaker for those of you who wouldn't happen to know him. So, since his PhD, Professor Minev, which he obtained at the University of Cambridge, Professor Minev research focused on stretchable electronics, and even in his later postdoc activity at the Center for Neuroprosthetics in EPFL, he aimed at developing soft implant for the nervous system. He has been research group leader at the Biological Center of Technical University of Dresden, and then he became professor at the University of Sheffield in the UK. Now in 2023, he was appointed as Kroner Professor for Electronic Tissue Technology at the Medical Faculty of the Technical University of Dresden and the Leibniz Institute for Polymer Research. So it's a pleasure to have him here. And before we start with the presentation, I would like to give some technical details. So we will have the talk from our presenter, and then we will have a 15 minutes Q&A session. For all of you who may have some question, I kindly invite you to provide them by the chat tab in Teams or the Q&A tab in your Teams application. And then I will proceed to read them to our guest during the Q&A session. With this, I will leave the floor to you, Ivan.
Okay. Well, thank you very much, Mauro, for the introduction, for the kind introduction, and also for the invitation to speak at the seminar series. It's great to be able to present a different, perhaps, every area of applications for bioprinting, and thank you everyone for tuning in and listening to my talk today. So I would begin by sharing the screen, of course. So please wait a second. Okay, so I hope you are now able to see the presentation.
Yes, we can.
Excellent, wonderful, thank you. Basically, just as I said, today I'm going to talk a little bit about the applications of 3D printing in the context of bioelectronic interfaces, but of course, I would like to quickly begin by giving a definition of what a bioelectronic interface is. So, in the simplest terms, this is a machine that has been engineered to establish a communication channel between a living system, a biological system, and let's say a computer. So, of course, these are complex systems. They have many dimensions. They could, they need, for example, software to program them. But of course, they need hardware. They need the physical devices that might be an implant or a wearable device that actually goes and contacts the biological system. And this is where we place our interest, and this is the kind of technologies we are trying to develop in my research group. So in the kind of approach we take is from materials to building systems to testing these systems in the biological scenarios, and typically we focus on three areas: brain-machine interfaces. These could be implantable devices, artificial skins, so e-skins that are sensors that are integrated on textile, for example, that is worn, or also in vitro platforms, interfacing systems that are designed to be placed inside cell cultures, for example. And as I said, we start with developing materials. Sometimes we formulate completely new materials. Sometimes we mix things that are available into composites. And once we have those attuned to our application, then we explore various microfabrication technologies to make devices out of them. And then these devices are then integrated in systems. And then these systems are then deployed in various models of disease, for example, in rodents, or in systems that are, we are pushing for translation into in medical technologies. So this is a broad overview of where we sort of place our activities in bioelectronics. But of course, another good way to understand bioelectronics is to look historically how things started, and maybe you can say that the beginnings were approximately 200 years ago, and at that time Alessandro Volta was experimenting with some batteries and was trying to stimulate his ears and eyes, and was reporting various perceptions that this electrical stimulation had on his body. And then a few decades later, people started to apply this in medicine. And there were really many types of ideas of how electrotherapy could be applied for basically to cure any kind of ailment that humans had. But of course, we know that this doesn't solve all problems. And even back in those early days, there were many different kinds of electrodes developed. So these are basically the devices that are placed on the body, and they used to really to inject currents into the nervous system, or to record the activity of these bioactive, electroactive tissues. And of course, maybe throughout the decades, things have progressed in different aspects in materials, and also in terms of fabrications, and also in what computer chips can do. And now in the early 21st century, there are many emerging technologies that rely on bioelectronic interfaces, and these often make it into the news. Maybe one of the latest was, from a group in EPFL in Switzerland. Brain implants help paralyzed people walk again, or they can be used to restore touch in amputees, so to basically feed signals into the nervous system that is used in neuroprosthetics. So there has been a steady development in this area. It complements technologies that are already out there in clinical practice. Examples of this are the cochlear implant or deep brain stimulation implants. So these emergent neuroelectronic interfaces really are resting on a very kind of solid foundation of historical technological development. And perhaps a little bit more in the introductory vein. So one of the key components in these bioelectronic interfaces is the electrode array. These electrode arrays can be placed in different locations in the nervous system. They can be adapted, for the anatomy of the area which they need to interface. And really, they are conceptually, at least, very simple devices. They consist of electrical conductors. Typically today, these are metals such as platinum or some alloys that will guide electrical currents to the place where we want to stimulate the nervous system. As you can see here, you have a number of contacts kind of arrayed on an insulating matrix. Same thing here. In this is a electrode array designed for the inner ear, for the cochlea. But again, we have a number of contacts that are dispersed in a silicon matrix, and then this is inserted. It really makes the contact with the nervous system. And the materials today, as I just mentioned, are typically based on silicones and metals. But we are going through in a way, a golden age of development for neuroelectronic materials. The idea is to use now materials that are more biocompatible, more similar to tissues in terms of mechanics, biology, and softness, for example. So there are many different ideas of how to incorporate hydrogels, biopolymers, or even living materials inside these electrode arrays, and make them in a way indistinguishable from biological tissues. And you know, here is a little bit of a representation of what we're looking for in terms of mechanical properties, and also what is available in terms of engineering materials which we can use to build our bioelectronic implants. So as you can see here on the spectrum of elastic moduli, the tissues which we are looking to interface, such as the brain, you know, or maybe muscle tissues, are extremely soft. They have elastic moduli on the order of hundreds of kilopascals to megapascals, and the engineering materials that can do this are classed as hydrogels, elastomers, or plastics. And this is important because when we put these devices, these implants in the body, we need to bear in mind that the body is dynamic. If we put something in the spinal cord, you know, these structures are constantly subject to mechanical loading, stretching, compression, and even inside the brain, we can see that the pulsatile flows in of blood create these micro motions. So we need basically to use materials that are soft, that can sort of survive these mechanical dynamic deformations that we are experiencing in a living, moving body, without this resulting in cracking and basically failure of the implanted devices. So in a way, this sets up a little bit the problematics here about what kind of device we need to make for a neural interface, what we need in terms of dimensions, electrical properties, and also mechanical and biological properties. And here, you know, one approach to make basically an electrical conductor that is elastic is to mix, to make composite, for example, by mixing platinum sand or microparticles with a silicone elastomer, and then, you know, create a composite that can be elongated, mechanically deformed. But because the particles inside remain in contact, we have a conductive, a material that survives mechanical deformation and remains electrically conductive. So something like this could be very useful for building you know, bioelectronic devices which fulfill the, you know, stringent criteria. So this is just an illustration. What you see here on the right is a cyclic voltammogram, just to indicate that you know, even when we deform this composite material made of platinum, we preserve its electrochemical signature. So that might be not a very conductive platinum in inverted commas, but still maintains a lot of its properties of the metal. Okay, so with this, I would like to move a little bit now into the area of printing, of course, when I started looking into various rapid prototyping technologies, the idea was that could we apply them to make our electrode arrays, to make the bioelectronic interfaces. And the reason for doing this was that you know, this will give us, first of all, an opportunity to process these soft materials in a kind of a platform that can handle multiple materials. But it also allows us to rapidly change designs and make things that are adapted for specific niches in the nervous system, or maybe one day be adapted for patients with different anatomies. So the region printer was very useful for us, because it allows us to combine these different printing tools into one platform that is integrated in a, I like to think of it as a little clean room. So essentially we have a laboratory in a box that enables us to produce these integrated systems that comprise of different materials needed for the bioelectronic device. And So in our current setup, we are able to print by extrusion, whether air-driven extrusion or volumetric extrusion, with different print heads. And this allows us typically to print silicones, so silicone rubbers that are typically extruded as a paste, and then this printed product is polymerized by different ways, but basically this paste then is polymerized to become an elastomer. And there are really different types of elastomers. Some of them have tuned optical properties, such as a different refractive index. They even reflective silicones. And shear thinning silicones, such as the one here, which enables us, really to push the material through very small nozzles. And some silicones we've formulated ourselves by making conductive composites. We are also able to use the inkjet functionality to produce, to handle basically inks of low viscosity that then can be combined with the structures printed in silicone. And one thing that is, I think, not a standard option is that we have implemented a plasma tool that is able to selectively change the surface properties, the wettability of our printed structures. To modulate the interaction of the liquid inks with the rest. So by using this kind of setup, as I said, this is a multi-tool printer that enables handling of multiple materials, a laboratory in a box. Here you see a small video of how we use the various tools. So this is the first thing you saw is how we can expose the surface to plasma. This is simple extrusion of silicone that defines essentially the insulating parts of the electrode arrays. And then if we zoom forward now, we switch to the self-friendly, I think that's the name of this print head, where we form droplets of the conductive ink, and we kind of fill the channels that are formed between the silicone tracks to form the electrical conductors. And then, the finished product, the finished electrode array, then might look like this. What you see here is an electrode array that's designed for the spinal cord, so that's why it is a little bit elongated. But the important sort of property of this is that it is elastic and stretchable, in a way mimicking the mechanical properties of the surrounding soft tissues around the spinal cord. This is a different design here. So these are single electrode shanks, so a single electrical conductor that are implanted in muscles and kind of stretch and move together with the muscles. Of course, all of this printed inside our kind of laboratory here. Okay, so was when we started printing, for first time, I came from a different microfabrication field. I was used to using soft lithography and spin coating, metal deposition, etching, and things like this. And at that time, I just thought that, we're going to start printing now, and we're just going to put any material in these printing nozzles. We're going to put a little bit of air pressure, and things are going to come out, and we can print anything that we want with perfect control. But of course, we soon realized that this is not going to be so easy, because there are many parameters that are playing in here. And I wanted to highlight here to you some of them. Of course, there is much that goes in the rheology of the inks. But a few years ago, there was some interesting literature about how the speed with which we print and the height of the nozzle and the sort of the speed of extrusion can affect the pattern that is produced. And in this paper, it was explored how to produce wavy structures or even coils when you're printing from far away and going slow. And then we use this a little bit as inspiration here to explore a different regime when we are printing actually very close to the substrate. And there are two parameters that have to be defined, the non-dimensional nozzle height and the non-dimensional nozzle speed. But basically these are one when we are when the height of the nozzle about the substrate is equal to its diameter. That's h star here, and v star is equal to 1 when the speed with which the material comes out is equal to the translational speed. But to cut a long story short, we explored parameters where the nozzle was going very close to the substrate and going very slowly. So and then we look at the cross section of the filament that is produced like this. So if we are going relatively fast and at a height close to 1, we can produce, of course, circular filaments. But like illustrated basically here. But then if we go a little bit lower and slower, we can start to flatten this filament and produce in a way something that looks like a ribbon. And if we go even slower and closer to the substrate, a groove is becoming, a groove starts to form in the extruded filament. And then we also observe that there is some regimes in which the walls of this groove can collapse in a way, forming a microfluidic channel. That is a kind of a standalone microfluidic channel. And we explored the phase space here and found that, by tuning these two parameters, V and H, we can decide in which of these structures we produce. And one of the materials that worked very well with this concept was this shear thinning silicone, Dowsil SC1700. But of course, other, also hydrogel materials we found were able to produce similar structures. But of course, this enabled us to produce some interesting demonstrations, such as microfluidics that are not integrated on a membrane, but rather as standalone fibers. Also, optical fibers when we fill the inside channel with another kind of silicone with different refractive index. We also make pneumatic actuators where we sort of combine an optical channel with a air channel. So when we inflate the air channel, we can sort of actuate this structure. But we soon found that this was probably not the most optimal way to make the fibers and the individual components. So we switched to a more how to say a classical layer by layer way of doing things. And without going too much into the details, a typical way to make let's say an electrode would be to start with printing one layer of material where a little area is left unexposed. This is going to be the active site of our device, and then continue with building further layers. That's going to create now in the second step a channel with a central lumen that opens then to the surface of the substrate, and then we can fill this this opening with something, with a conductive ink, with a optical silicone, or we can leave it empty if we want to deliver a fluid through this channel. And of course, at the end, we need to do something to be able to close the top layer of this device. We were able to, as I said, produce multimodal devices that not only for electrical recording stimulation, but optical and chemical exchange. or stimulation of the biological systems. And again, a little bit of detail on fabrication process for making an electrode arrays on demand with layouts that can be tuned. But generally, the process proceeds as follows. We use the shear thinning silicone to produce the insulating parts of the electrode array, and then we use the inkjet functionality to fill the channels with conductive inks. And in our case, we use a two-step process of forming the conductive ink. So we use a dispersion of platinum nanoparticles in a solvent, and we jet this into the channels, and then we evaporate the solvent. So this creates, in a way, a platinum sand of microparticles inside these grooves. And then we can flood this with extra silicone, which kind of penetrates in between the particles and creates a composite material in situ that again is blended with the rest of the device, with the rest of the silicone components of the device. It has electrical conductivity but survives mechanical stretch because it is a composite. And we use this to produce a library of electrode arrays that could be, you know, easily changed in terms of where the individual electrodes are placed. We worked with various preclinical models such as rats. We also tried to do this in fish. We were able to implant small electrodes in the swimming muscles of the fish and stimulate and control which way the fish is bending. But you know, the take-home message here is that you know, this printing approach to the electrode array, you know, it creates an accessible preclinical technology. That means that, you know, it's easy for somebody to test a design where they think, you know, I want to treat this disease, but you know, I need a specialized implant for this. That might be an easy way to, easier way to create such bespoke devices. And of course, maybe in the long term, when this gets into clinical practice, it might offer a way to personalize the implant and adapt it to a specific patient. Okay, so this is an application that I wanted to show a little bit more into the detail. Again, this is an electrode array that was implanted on the surface of the brain in rats, and it had a couple of electrodes for recording and stimulation, you can see here, but it also has a microfluidic channel to inject drugs in the brain and see how they affect the electrical activity. Maybe just here, if we focus, what this shows is that the device is able to record these event-related potentials, so these electrical signals that are generated by the cortex, and they're different depending on what the rat is thinking or doing. And what is shown here is that, you know, when the rat hears an unexpected sound, then this creates a brain wave, if you wish, that is different than the brain wave that is created when the rat hears something that is used to. So this demonstrates the utility of this technology as a research tool, maybe to understand a little bit better how the brain processes information. Another application of this integrated, you know, printed sensor actuator arrays is for cell culture, and here we made something that has electrodes and microfluidics for drug delivery, and we printed this as a cell culture platform. We use the printed optical fiber to deliver light and stimulate cells using optogenetics, deliver a drug, and at the same time record the electrical activity of the cell culture that is formed on the surface here. Without going much into the detail, this allows us to make multimodal interfaces and really stimulate in different modalities, recording electrical modality. And one of the latest projects that we've started now is in the area of wearable technologies. Here there is clinical need for tracking and monitoring the health of the hand, for example, in recovery post-stroke, or for monitoring neurodegenerative conditions. It would be good to have quantitative data on how things are progressing. And so here we aim to basically print various sensors on cotton textile. So the patient wears this, makes a few exercises, and we get quantitative data on the health of the hand. So the idea is, you know, the patient wears the glove, the neurologist marks the location of where these sensors and actuators need to be placed, and then we put the glove on our printer. We find the locations where the sensors needs to be. We create a design, and then we just print this array of sensors and actuators, on this planarized glove. And then once everything is done, the glove is baked, polymerized, and then we put it on and measure signals from the various sensors. Again, in the interest of time, I will try to be quick here, but this is a very simple process. This is intentionally, we wanted to make this a simple material process in a simple way. So we simply mix graphite flakes with silicone, and then the resultant ink could be printed by extrusion. Best is volumetric extrusion, works best. And then, you know, this gets integrated directly on textile. We find that the material blends and kind of fuses a little bit with the threads in the textile, so adhesion is pretty good between composite and textile. By changing the amount of graphite flakes, we can change the conductivity, you know, with reasonably good control. And also this, because it's still a composite, it remains mechanically elastic, so it continues to function, to conduct electricity. It's stretched, which could be used as a sensor. And then this allows us to print three types of sensors, so multiple modes of sensing could be realized. What you see here is a pressure sensor. When you put pressure on this kind of structure, you know, we detect a change in resistance. This is another type of sensor, which is a stretch sensor. Again, here elongation produces the change of resistance. And to record the muscle activity, we place electrodes again on the glove, and here this is the opponent's pollicis muscle here, which is responsible for movement of the thumb. This of course allows us to simultaneously monitor the various sensors. What you see here, for example, in P4 and P5, you know, is thermal position here with weak force and here with strong force. And when we look at the record of the sensors here, we see, you know, the pressure is stronger the second time pressed with more force. A similar kind of movement in the strain sensor, and a little bit more power in terms of EMG activity from the muscle is recorded when we press strong. Okay, in the interest of time, I probably have another minute, if I may. I just wanted to say that we're also interested in finding out new ways to print new materials, for example, based on electrochemical printing, where we can handle small liquids on conductive surfaces and actuate the nozzle in order to polymerize hydrogels in different conductive surfaces. We can make arrays of dots, or other continuous patterns. We can print with conductive polymers such as PDOT, combining with hydrogels, you know, and really do this on flexible and conductive substrates. So this is a little bit of a, you know, to show where we think we can go with combining yet more printing tools and printing modalities into this system, this 3D printing system. And with this, I've reached the conclusions, and really in one sentence, so the printing technologies can enable rapid design iterations for bioelectronic devices it does create arrays of soft sensors and actuators that can operate in multiple modalities beyond electricity, mechanical, optical, etc., that can enable bioelectronics as implants, wearables, or in vitro interfacing of biological systems. With this, of course, I would like to thank the people who actually made the research. Here is the group in Sheffield, and at the bottom is a historical photo from my group in Dresden. Various collaborators in Germany, in the UK, and of course the funding sources, the ERC, and the Freigeist Foundation, as well as the institutions. Thank you very much for your attention, and I'm looking forward to questions.
And thank you, Ivan, for the really wonderful presentation. So, now I, of course, open the floor to questions. As I said before, you can either use the chat tab or the Q&A tab of Microsoft Teams. And so first one is from Gianluca, and I wanted to confirm you that the registration of the talk will be available will provide on our channel, so you can, for those who missed it or want to catch up again on some particular aspects that I've missed, it will be available on all our channels. While we wait for other questions, maybe I can break the ice with a couple of them. First one is more of a small curiosity on the materials. So you work a lot on silicon formulation, and I wanted to ask you, of course, you may have tested many, if you encountered any issues in terms of printability window if you use single component or bi-component, so you have the reticulation happening in print, or if you tried other methods such as embedded printing for low viscosity formulation.
Mm-hmm. Yes, so absolutely. So this, so I think the first question relates on polymerization during the printing process, and of course we have noticed that if we print for hours, then that would start happening. Some time ago we quantified a little bit how things shift in time, but we do have a reasonably long window of at least 1 to 3 hours of printing without things starting to change a lot. And of course, once we load the cartridges, we keep them in freezers when we are not printing. There are also other systems where polymerization is induced by contact with moisture from the atmosphere, and that's another way to kind of keep things in a syringe without exposing them to these cues for polymerization. Of course, in silicones, you have a very wide range of materials to choose from. And in the other question that relates to printing in a support medium, this is something that I am aware, but we haven't done this before. That might be quite interesting for printing with the well-known PDMS material that is known to be, of course, very flowable, very low surface tension, but this could be a nice way to restrict it somewhere. Yeah.
Perfect. Thank you. And maybe while I got the word, I can try to squeeze in another one.
Oh, yeah.
So, of course, this field of application compared to other application of bioprinting is probably one of the closest to actual translation in terms of requirement, also legislation, compared to use of living cells embedded in the printing process. So I wanted to ask you if you already have made some step or just started thinking about this translation step, and if you can share some consideration also in terms of, I don't know, which are the limitation approved material for in the end, some of these applications are also internal implants, not only wearables, so maybe the situation changes drastically.
Yeah, of course, for the wearable devices, it is much easier to do because you know the level for the threshold for entering is lower. There's no implant, but we still have to make sure that these materials do not cause irritation. But I think the most logical way to translate some of this is through wearable devices. But of course, if it's implants, again, platinum is a well-known material that is approved for implantation. Of course, there are many silicones that are the same. But of course, these are done in a different form. These are composites, so it takes a while to get there. But having said that, I know that there are others that have done excellent work in translating and actually, similar kind of composites, silicones and conductive microparticles for implants. So I think that these materials are going to be more known in the field, which might help adding the printing aspect as well.
Okay, thank you a lot for sharing this aspect. And maybe a few words on so the application of textiles and wearables. Do you plan also to include some other elements for the recording? And so have you done some work in that direction in terms of integration with, I don't know, external recording for telemedicine application or similar?
So one interesting note here to say is that one overlooked element of this system is the connector. So that is basically the thing that links this soft textile stretchy circuit to the external electronics that is a rigid chip, basically, or a PCB or something that is not so flexible, stretchable. So we've spent a lot of time to figure out how to make this connector, but now we're at a stage where the output of the sensor can be taken to a ribbon cable that can be used then together with a ZIF connector to plug into a PCB, and we are actually doing some work on the acquisition electronics for this, but it's just simply too early to show.
Perfect. Okay, I will say with this we reached our 1 hour. I monopolized a bit your attention, but thank you a lot for all your answers. And so again, it has been a pleasure having you here, and really congratulations for all the wonderful application that you showed us today.
Thank you very much, Amaro, and again once more for the invitation and for everybody who joined us today. Thank you for your attention.
Perfect. And thank you all for attending, and wish you all a nice day. Goodbye.
Thank you. Bye.